We are discussing today at another chapter from electricity, that is thermoelectricity as such. One of the smallest chapters of electricity, which of course is going to fetch you one question in the final EAMCET paper. And more or less I should say very few formulae we have in this particular chapter, and of course the formulae also can be easily remembered and the problems are also easy to work out with. So this is the chapter what we are taking up today. Before taking up the applications of this thermoelectricity, let me remind you some of the important concepts of this chapter. Thermoelectricity, the basic idea has been taken from Joule's law. That law, of course, all of us we know, W is equal to JH, where J is called mechanical equivalent of heat and H is called heat energy generated and W is the work. This heat, of course, we otherwise call it as Joule heat also. This Joule heat is irreversible. Remember that. That is one point to be noted. Coming to the second one, according to the concept of Seebeck effect, we people can understand whenever a thermocouple made up of two different metals are maintained at different temperatures, such as one at 0 and one at T degree centigrade. Let us say this is iron, this is copper. One is said to be a cold junction and other one is said to be a hot junction. This pair of metals, whatever we are taking up here, is called a thermocouple. Whenever temperature difference is maintained across the thermocouple, thermo EMF is going to be generated across the system. What is this thermo EMF by formula? It is AT plus BT square. That is the general equation we used to take up. What is what out of that? This T is nothing other than temperature of hot junction, and A as well as B, these two are called thermocouple constants. That is actually the concept. So for this particular equation, when we just plot a graph taking the temperature of hot junction on x-axis and the thermo EMF that is generated along y-axis, then what kind of a graph we obtain, you all are familiar with. A parabola type of a graph we get, that's one. And if I take this one is temperature of hot junction, that is one point that is taken on x-axis, and this is what we call it as thermo EMF that is generated across the thermocouple. So if I take, this is going to be the temperature of hot junction at which the EMF generated over here is maximum. So you can all understand the corresponding temperature of hot junction at maximum EMF is called neutral temperature. This neutral temperature officially is the characteristic temperature of a thermocouple. Means what? For a particular thermocouple, neutral temperature does not vary. It is going to be constant. Whereas this one, if I take the temperature of hot junction at which the EMF is becoming 0 or beyond which the EMF reverses its direction, this is what we call it as inversion temperature or temperature of inversion. And if I take this as the temperature of the cold junction, then due to the symmetry of this graph, the difference between these two temperatures and the difference between these two temperatures are going to be equal. Means what we should write now? Tn minus Tc is equal to Ti minus Tn. In other words, T neutral is equal to inversion temperature plus cold junction temperature by 2. This is one formula you have to remember. Under this a small condition, if cold junction temperature is maintained at 0 degree centigrade, then you can directly write inversion temperature is twice neutral temperature. Or you can even write the same thing, neutral temperature is half of the inversion temperature. So this is one more part you have to remember. Coming to the next one, this particular graph can be represented by this equation AT plus BT square. I have already told you that point. A and B are called thermocouple constants and T represents the temperature of hot junction. Now there are two important most conditions you can obtain from that equation. The very first condition is this: at maximum EMF, all of you should understand, maximum EMF, what is the condition? Thermoelectric power, that's what we used to take it as, thermoelectric power, that will be 0. What is thermoelectric power? dE by dt will be 0 at maximum temperature, EMF. At maximum EMF means what is the corresponding temperature? We know that is neutral temperature. If I take dE by dt from that equation, is it not A plus 2BT? That T now is to be called neutral temperature, and this value should be 0 at this particular maximum value of EMF. So what is the equation for neutral temperature from this? Minus A by 2B. This is the equation for neutral temperature from that equation of EMF given. And secondly, you can even write this way: at inversion temperature. You can definitely understand inversion temperature is that temperature at which the thermo EMF is becoming 0. So at inversion temperature, EMF will be 0. EMF will be 0 means what? AT plus BT square will be 0. This is called inversion temperature. One T you can cancel that one. So T inversion is equal to minus A by B. This is another formula you have to remember. So one equation for inversion temperature, one equation for neutral temperature, and other equation what I have already written, that is the relation between neutral temperature, inversion temperature and cold junction temperature, which is Tn is equal to Ti plus Tc by 2. That is the point. Now come to one more theoretical question. For any thermocouple, neutral temperature is independent of cold junction temperature, whereas inversion temperature depends on cold junction temperature. For example, if the same graph if I get like this, then you can definitely understand this in cold junction temperature is increasing and inversion temperature is going to be decreased correspondingly. That means what? The inversion temperature definitely depends on cold junction temperature, whereas neutral temperature does not depend on cold junction temperature. So these are few formulae you have to take up first. Come to the next one. Whatever thermoelectric power you people have taken up just now, that thermoelectric power is also called Seebeck coefficient also. That is the concept. So Seebeck coefficient's other name is what? Thermoelectric power. That is the concept. So how do we represent this one? Yes, this power means P. What is that one officially? dE by dt. That is what is called power or Seebeck coefficient you can call it. So what is its formula officially? A plus 2BT. So at times they may ask you to calculate Seebeck coefficient. That time this is the formula by means of which we can estimate that value. That is one. What is the next one here? That is regarding Peltier effect. In fact, Peltier effect is simple converse of Seebeck effect. When we are applying temperature difference, we are getting EMF in Seebeck concept. Whereas in Peltier effect it is the other way. When you apply potential difference across the junctions of a thermocouple, automatically heat is going to be absorbed at one junction and evolved at the other junction. Thereby, the temperature difference automatically is going to be created across the junctions there. That is the concept of Peltier effect. But what is important over here is, what is this Peltier coefficient? This is of course one based on which in earlier EAMCET papers they have asked problems. Peltier coefficient generally will be represented by pi. Don't think that pi is 22 by 7 or 3.14. It is a constant for a particular thermocouple. So Peltier coefficient is represented by pi is equal to quantity of heat energy evolved or absorbed per unit charge that is passing through that particular junction or that thermocouple as such. This in other words I can write this way also, Q by current into time also. Q will be in joule, This small q will be in coulomb. Joule per coulomb is also called volt. So what you should understand? Peltier coefficient of a thermocouple is nothing other than or numerically equals to the potential difference across the junctions of the thermocouple. So Peltier coefficient and potential difference both have the same units, same dimensional formula. That is the point we have to remember. Now according to Thomson, not alone at the junctions we will be getting that heat is evolved or absorbed. Throughout the length of that particular conductor, at several points, heat absorption takes place and heat evolution also takes place. So what is this Thomson coefficient? Thomson coefficient. What is this? Actually, we represent this one by the value of sigma. What is this Thomson coefficient here? Sigma is equal to Q by small q into delta T. What is this Q? Of course, we know that is charge. This capital Q is quantity of heat absorbed or evolved. What is the delta T over here? Variation in temperature across those 2 points where you are calculating the value of Thomson coefficient. This, in other words, you can even write it like this also. Capital Q by I into small t into delta T. This is time small t and delta T is variation in temperature over there. This is the concept. And of course, we all know very well, there is one particular series of different metals they have given, which is called thermoelectric series. Antimony is going to be the first metal. Afterwards, of course, iron, lead, like that will be having the chain. The middle one almost is lead over here. And coming to the last one over here is bismuth. I just want to focus on the end elements and the middle element. So antimony, lead and bismuth, in between we are having few more metals and all, we can understand. Before this lead, whatever the metals we have up to antimony, they are called thermoelectrically positive metals. After the lead, whatever we are having up to bismuth, they are called thermoelectrically negative metals. Second point, any 2 metals out of the chain, if you consider and if you construct a thermocouple, the current across the thermocouple will be from the element that appears first to the element that appears later across the cold junction. For example, antimony lead thermocouple if I construct, then the direction of current will be from antimony to lead across the cold junction. That means lead to antimony across the hot junction. That is the second point. Coming to the last point here, more is the gap between the elements in the particular series, greater will be the produced thermo EMF. So what you should understand, this is the first element and this is the last element. Therefore, if you can construct a thermocouple using the end elements, whatever the thermo EMF you are going to come across or find across the system, that is ultimate and that is the highest. So these are the points one has to remember as far as thermoelectricity that's concerned. One of the easiest chapters we have, and of course most of the problems look alike, but calculation wise slightly there may be a deviation there. So let us start taking up some of the problems based on this particular chapter, thermoelectricity, please. Look at the very first problem. In fact, there is a theoretical question, there is nothing in that. Thermo EMF produced in a thermocouple does not depend on, first of all, it depends on what you identify. It depends on the metals taken in the thermocouple. It depends on the Thomson coefficients of the metals in the thermocouple. It depends on the temperature of the junctions. What exactly the temperature difference across the junctions also is one of the criteria based on which thermo EMF that is generated over there. But it does not depend on the fourth one what has been mentioned there in that problem. The duration of the time for which the current is passed through the thermocouple. How long you are passing current is immaterial. Whether you pass for 1 minute or 1 hour, hardly that matters. Thermo EMF generated simply depends on first, second and third, but it does not depend on the fourth one. So that itself is the correct option for this particular question number 1. So that is the first one. Look at the second problem, please. What is it you are getting? The thermo EMF in lead iron thermocouple with one junction at 0 degree centigrade is given by E is equal to 1784 T minus BT square in volt, where T degree centigrade is the temperature of the other junction. If a neutral temperature is 371.7 degrees centigrade, then the value of B in volt per degree centigrade square is how much? First of all, let us write the formula. E is 1784 T, that is the first term, minus BT square, that is the one. Now he is giving us neutral temperature is 371.7. So neutral temperature 371.7 degrees centigrade he gave, fine. But we know according to the formula, neutral temperature is minus A by 2B. That is the formula what we have. This is the value of A. And this is of course B. We know that one very well. So minus A by 2B when you talk about minus 1784 by 2B. That value is equal to how much now given? 371.7. So what can we write now? 2B is equal to minus 1784 by 371.7. This is actually the concept. But our concept is only B I want. So minus 1784 by 2 times this one. 2 7 is 14, it's 1. 2 1 is 2 1 plus 1 3. 2 7 is 14, that's 1, it is now 7. 743, just look at carefully, 743, it cannot be cancelled 3 times in 1784. So it will definitely be above 2 times. So out of all the 4 options, it is given 2.4 is the nearby answer for us. So what is the value of B now? It's minus 2.4 over here. That is actually the concept. Already minus sign is here. So you can directly take this one as 2.4 also. But according to the values given, you just have to go for the second option for this question number 2. Look at the next number, that is problem number 3 please. The thermo EMF of a hypothetical thermocouple varies with temperature theta of hot junction as E is equal to A theta plus B theta square in volts, where the ratio of A by B is 700 degrees centigrade. If the cold junction is kept at 0 degrees centigrade, then the neutral temperature is. Same question has been asked in one of the EAMCET papers earlier. A very controversial question in fact in one way, but okay, that method what he has mentioned is appreciable. E is equal to A theta plus B theta square, that is the equation mentioned for us. No doubt about that, he is giving us what is the neutral temperature is the question he is asking. Neutral temperature is minus A by B. Officially, that is the formula actually I have told you, minus A by 2B. But what is the value as mentioned? A by B is given 700 degrees centigrade. Look at this value carefully. When A by B is 700 degrees, then what will be the neutral temperature according to this formula please? Minus 1 by 2 into 700 degrees centigrade. That of course is minus 350 degrees centigrade, fine. But you all know well, when he is talking about that cold junction of course is at 0 degrees. Is there any possibility for us to get a neutral temperature less than 0 please? Is that one possible? No, not at all. Because when cold junction is at 0 degrees, neutral temperature should be much higher than 0. Inversion temperature will definitely be 2 times the neutral temperature. These are the results of course we have already seen just now. Therefore, the correct answer for this particular problem given at EAMCET is the 4th one. Look at carefully. No neutral temperature is possible for this thermocouple. Of course, he has mentioned in the very beginning of the problem, hypothetical thermocouple. Hypothetical means which is not going to exist. It's very simple concept. But as he has given you some values, according to those values, you cannot obtain any value of neutral temperature there. So, 4th option is the correct option for this particular question number 3. Look at the next one, that is problem number 4. In a thermocouple, cold junction is at 0 degrees centigrade and hot junction is at T degrees centigrade. The graph drawn between thermo EMF and temperature of hot junction is represented by the equation E is equal to AT plus BT square. If A is equal to minus 224B, the neutral and inversion temperatures of the thermocouple respectively are. Even this question also has been given in the previous EAMCET papers. So, if you look at the equation given first of all, E is equal to AT plus BT square. That is what has been mentioned. And what else he has given you? A is equal to, he has given minus 224B. That in other words, you can say A by B is equal to minus 224. This is the value provided for us in the problem. Now take this equation as it is. What is our first question? What is neutral temperature? In fact, neutral temperature is going to be minus A by 2B. That is actually the formula from this equation. We know that one. So, minus A by 2B, can't you just write minus 1 by 2 into A by B, please? You can rewrite like that. Now, substitute this given value over there. Minus 1 by 2 into minus 224. So, what is it you people are going to get directly here? 2 cancels here, 112 times, minus of minus becomes plus. So, 112 degrees, this actually is the neutral temperature for us. In fact, 112 degrees out of all the 4 options, in the third option, the first option itself is given that way. So, third option must be correct. But what else we just want? What is neutral temperature? This is twice inversion temperature, that is 224 degrees centigrade. So, what should be the correct pair of options that is correct over here? 112 degrees centigrade for neutral temperature, 224 degrees centigrade for inversion temperature, that is correct. That means third option is the correct option for this problem number 4. Look at the next number, that is problem number 5. The thermo EMF of a thermocouple is given by E is equal to AT plus BT square, where A by B is minus 200 degrees centigrade. If the cold junction is kept at 30 degrees centigrade, then the inversion temperature is how much? But carefully observe the problem. Option values are given in degree centigrade. Options are mentioned in Kelvin. So, ultimately what is it you have to do? After getting your answer in degree centigrade, you have to convert that value into degree Kelvin, that is into Kelvin. Absolute scale you have to convert that one into. So, AT plus BT square, that in fact is the value, that is the equation for thermo EMF given. E is equal to AT plus BT square, that is given, fine. What else he has mentioned? A by B is equal to minus 200, he said. That's fine. Now, according to this one, what is our first question? What is the temperature of inversion he is asking? The cold junction is at 30 degrees, then the temperature of inversion or inversion temperature is how much? In fact, inversion temperature is minus A by B. That is the formula. We people can certainly understand. Right, that is the concept officially. But what you need to remember in this case, officially minus A by B means minus of 200 with minus sign once again. But be a little careful. I have already told you, when we talk about the graph, when cold junction is at 0, this is inversion temperature. When cold junction increases, inversion temperature automatically decreases. So, what you will be finding over here now? It will be less by 30. That means what will be the correct value to be taken over here? It's minus of minus 170. That is the concept. So, how much is the value here? 170 degrees centigrade. But of course, he is asking you the answer in what? Kelvin. So, you have to add 273 to that. Then what will be your answer? 3 here, 4 here and 4 here. 443 Kelvin. See that option number 4, that is going to be the correct option. By any chance, if you are unable to see that Kelvin carefully there, you may even leave that one here like, but of course he has not given any answer as 170. But one should be careful in identifying the correct option there. Look at the next problem, problem number 6 this time. For a thermocouple, the temperature of cold junction, neutral temperature and temperature of inversion are given 0 degrees centigrade, 285 degrees centigrade, 585 degrees centigrade respectively. If the temperature of cold junction is raised to 10 degrees centigrade, then neutral temperature and inversion temperature, these two are the questions he is asking us. One thing, let me write the values first of all. Temperature of cold junction is maintained at 0 degrees. Neutral temperature is given as 285 degrees centigrade. So firstly you take till this extent. You can all understand directly neutral temperature is independent of cold junction temperature. Already I have repeated that point in the theory as well today. That means neutral temperature does not depend on the cold junction temperature. That means whether cold junction is at 0 degrees or at 10 degrees or 20 degrees, whatever be the temperature of cold junction, this value will not be varied. So your answer for neutral temperature should be 285 only. Remember that point first of all. In fact, with that option you can identify the right option in the problem. What is that? Third option is the correct one, no doubt about it. But there is a second half in the problem. Let us even work out that one also. We know very well neutral temperature is equal to inversion temperature, right, plus cold junction temperature by 2. That was the equation what I have already told you. So what will be inversion temperature from this one? Twice neutral temperature minus cold junction temperature. Now what is neutral temperature we have got? 2 times 285 minus cold junction temperature present value is how much? It is given 10. So you will be getting 400, 560, 570 minus 10. Of course in degrees only we people are getting. So what will be this answer now? 560 degrees centigrade. So inversion temperature will be 560. Neutral temperature must be 285. Whichever option that is having both the values, that option is the right option for us. That is the third option, which is the correct option for this question number 6. Look at the next number, that is 7. If the cold junction is held at 0 degrees centigrade, thermo EMF V of the thermocouple varies as V is equal to 10 into 10 power minus 6 T minus 1 by 40 into 10 power minus 6 T square, right, where T is the temperature of the hot junction in degrees centigrade, the neutral temperature and maximum value of thermo EMF are respectively. That is the point. Look at the equation what has been mentioned first. What is the equation given? He is talking about V is equal to, that is EMF, 10 into 10 power minus 6 into T, right, minus 1 by 40, that's okay, into 10 power minus 6 T square. That is the actual formula. That is the equation mentioned. What are the values we want? First neutral temperature we want. You can directly write this V is equal to AT minus BT square, like you can compare. This is the known equation, this is the given equation. So here A must be this one here, here B must be this one here. So what will be the neutral temperature? It's minus A by 2B. That is the formula officially. So minus A means 10 into 10 power minus 6 by, what is B? 2 times B, 1 by 40 into 10 power minus 6 with a negative sign. That should not be forgotten here. So cut this one over here. Directly you will be getting this one 10, this goes 20 times. 10 power minus 6 gets cancelled. 20 directly goes to the numerator. You will be left with 200 degree centigrade. So one option we have got out of that 200 degrees centigrade. But what is the next question? Be careful about maximum value of thermo EMF. When will the EMF be maximum? When this temperature is neutral temperature, then the EMF is going to be maximum. So what will be V maximum? That is the question. Take as it is the given equation, but in place of T, you substitute the value of neutral temperature. So what should we write now? 10 into 10 power minus 6, it is 10 power minus 5 into neutral temperature, that is 200, minus 1 by 40 into 10 power minus 6 into T square, neutral temperature whole square, 200 whole square, 4 into 10 to the power 4. Now you can directly cut this one 10 times over here first. This 10 cancels over here thrice. This now gets cancelled 10 power minus 3 times. Now even you can cut these two zeros also 10 power minus 3. So what is left over? You look at 2 into 10 power minus 3 minus 1 into 10 power minus 3. If you take 10 power minus 3 common, is it not 1 into 10 power minus 3 that is left over, please? 10 power minus 3 volt, is it not to be called 1 millivolt, please? So what are the options now? 200 degrees centigrade must be the neutral temperature, 1 millivolt must be the maximum value of thermo EMF. So which option that is having these two values? You look at fourth option has got 200 as well as 1 millivolt. So the option for this question number 7 is the fourth one, please. Look at the next problem, that is problem number 8. Once again it is a theoretical question. Consider the following statements A and B and identify the correct answer given below. Peltier coefficient is numerically equal to the potential difference across the junctions of a thermocouple through which current is flowing. I have already told you that point while discussing the Peltier coefficient. Peltier coefficient is 100%. It is numerically equal to the PD or potential difference across the junctions of a thermocouple. So statement A is 100% correct. According to Thomson, energy is neither absorbed nor evolved at the junctions of a thermocouple, but is absorbed or evolved only along the lengths of both the conductors. Thomson did not say that one. Actually what Thomson said is, throughout its length, at many a number of points heat evolution takes place. At many a number of points heat absorption that takes place. Not necessarily be only along the length, not at the junctions like. So that particular statement has not been given properly. So second one is not going to be correct. That in the sense A is correct and B is false. So which option is correct ultimately? Third option is going to be correct for question number 8. So A is true and B is false for this. Look at the next number, that is problem number 9 now. Look at the values. The hot and cold junctions of iron platinum and constant platinum thermocouples, when held at a temperature difference of 100 degrees centigrade, generate thermo EMFs of 1600 microvolt and minus 3400 microvolt respectively. The value of the EMF for iron constant thermocouple in microvolt per degree centigrade is how much? That is the concept now. Look at this particular value. The problem what has been given here is based on the law of intermediate metals. Now you look at the values given first of all. What he said? It generates thermo EMFs. Iron platinum gives 1600 microvolt. That has been given here. That is iron platinum. So I take iron here, platinum here. And of course what is the next one? That is constant and platinum thermocouple gives 3400 microvolt with a negative sign. That of course you can write this way. EMF, what is the order you see carefully? Constant here and of course platinum here. This is the concept. Now this is iron platinum, constant platinum. But what is it we want? Iron platinum we just want. Look at that final wording. What is for iron constant? Iron constant we just want. So iron versus constant. That is the thermocouple what has been constructed here. Iron constant I want. Officially according to the law of intermediate metals, this is equal to EMF across iron platinum plus EMF across platinum and constant. The order you see carefully. Iron platinum, platinum constant. Ultimately you get iron constant combination. But here he has given just opposite. Constant and platinum is given 3400. So what you can understand, this implies EMF across platinum constant, that will now be minus of minus 3400. How much it will now be? Plus 3400. So what you can write here? 1600 plus 3400. Ultimately you are left with 5000 microvolt. That is the concept. But of course, he is giving you this much of voltage for how much temperature difference, please? For what temperature difference is the potential difference? For 100 degrees, this is the value. But his question is microvolt per degree centigrade I want. So this implies 5000 divided by 100 microvolt per degree centigrade. Two zeros, if you cancel them, what will be left over? 50 microvolt per degree centigrade. This should be your answer. So what is the correct option once again for this problem 9 you look at? It is the fourth option again, 50. But of course 5000 also will be correct. If he asks you the question for 100 degree centigrade temperature difference, what is the total EMF? That is the point. Now here per degree centigrade he is asking, therefore dividing the value by 100, you will be getting the correct answer for this. Look at the next problem, problem number 10 this time. Once again, a theoretical question which has been given in earlier EAMCET paper. Assertion: rapidly changing temperature can be measured by thermocouples. In fact, thermocouples are very useful thermometers as well. In what sense? Minutest values of variations in the values of heat energy you can directly measure in terms of temperature. And using a thermocouple thermometer, you can even measure the temperature of an insect also. So assertion is correct. The thermal capacity of the junction of a thermocouple is very small. It is this particular reason due to which one can measure very rapidly changing temperatures using a thermocouple. So assertion is correct. Reason also is correct. Reason is 100% the reason for the assertion. So first option is going to be true for this. Both A and R are true, and R is correct explanation of A. That is for 10th question as such. Look at the next one, that is problem number 11. The thermo EMF produced in a thermocouple is 3 microvolt per degree centigrade. If the temperature of the cold junction is 20 degrees centigrade and the thermo EMF is 0.3 microvolt, the temperature of hot junction will be how much? In fact, that 0.3 must be millivolt. It should not be microvolt there. What for means? Micro means 10 to the power minus 6. Your answer should have 4 to 5 zeros there. But 2 zeros only you are finding 80, 100, 120, 140 like. So that 0.3 must be millivolt. Okay, let us see what exactly the concept we can take up. Now, what are the values he is giving us? Let us check that one now. The first one, 3 microvolt per degree centigrade. That means 3 into 10 to the power minus 6 volt. When this is the case, what is the temperature difference we are finding across the system? 1 degree centigrade. Fine. Now, what is the next question he is asking? 0.3 microvolt. What is the concept? The temperature of hot junction will be how much? That is the concept. 0.3 microvolt, that is 0.3 into, that is milli, minus 3 volt, it is how much? Then what can we write? 0.3 into 10 power minus 3 by 3 into 10 power minus 6. This in other words you can say 3 into 10 power minus 4 by 3 into 10 power minus 6. Cut this one over here. This one minus 2 times. So 100 you will be getting as the difference between the temperatures of the junctions. Now for example, if cold junction at 0, hot junction will definitely be at 100 degrees because the difference must be 100. Fine. Now the question, if suppose cold junction is at 1 degree, what should be this temperature of hot junction? It should definitely be 101 degrees. Why should it be? The difference once again should be 100 only. Now according to the given problem, if cold junction is at 20 degrees centigrade, for having a 100 degrees temperature difference, what should be the temperature of hot junction? It should definitely be 120, so that the difference of these two will now be equal to 100. So what is the correct option for you? The hot junction will be at a temperature of 120 degrees centigrade. So third option is going to be the correct option for this question. Look at the next one, that is problem number 12 this time. The cold junction of a thermocouple is at 0 degrees centigrade. Thermo EMF produced in the thermocouple is given by E is equal to 16T minus 0.04 T square, where T is the temperature of hot junction, the temperature of inversion and neutral temperature of the thermocouple R. This also has been one of the EAMCET problems of earlier years. So look at that equation given first of all, E is equal to 16t minus 0.04 t square. Now first of all you tell, now by this time you are all familiar with the formula. What is neutral temperature? Minus A by 2B. So minus 16 by 2 times B, 4 into 10 power minus 2 with a negative sign. Minus gets cancelled. 2 for the 8, that goes twice. So 10 power minus 2 going up, it now becomes 200 degrees centigrade. So neutral temperature must be 200 degrees. Then what will be inversion temperature? Twice neutral temperature. So that should be 400 degrees centigrade. But see the order what he is asking in the question. First inversion temperature, then neutral temperature is asking. So first one must be 400, second one must be 200. In that order, you see the second option please, 400 and 200. That is the correct answer. But don't be confused by taking the first one. First answer also is correct. But he gave the order 200 and 400. So inversion is not 200. Inversion is 400. So second option is going to be correct for this question number 12 please. Look at the next one, that is problem number 13. Thomson coefficient of a conductor is 10 microvolt per Kelvin. The two ends of it are kept at 50 degrees centigrade and 60 degrees centigrade respectively. Amount of heat absorbed by the conductor when a charge 10 coulomb flows through it is how much? Thomson coefficient, just now I have given you sigma it is. Sigma is equal to Q by small q into delta T. That is actually the point. But what is his question? What is capital Q the question? Sigma into Q into delta T. I can write. What is sigma value mentioned there? 10 microvolt per Kelvin. That is Thomson coefficient. 10 micro. That is 10 power minus 6. I can write. What is the charge that has been given to that one? 10 coulomb charge is flowing across. What is the temperature difference? 50 degrees centigrade and 60 degrees centigrade. So what is the gap between them again? Again 10, 50 to 60, 10 degrees. So 3 zeros you can cut them here, minus 3 times. So 10 to the power minus 3, what? The values what he is talking about in units of work. So joule. So you can directly write the value 10 power minus 3 joule. 10 power minus 3 is also called milli. Therefore 1 millijoule must be your answer, which is again the fourth option for this question number 13. Look at the next one, that is problem number 14 this time. An EMF of 0.09 volt is generated when the temperature difference between the junctions of a thermocouple is 75 Kelvin. If the cold junction temperature increases by 15 Kelvin, the percentage change in EMF is a wonderful question in fact. Suppose if I want change of EMF by original EMF, that is what is called fractional change in EMF, suppose I want. Is it not proportional to change in temperature by original temperature please? So what is the value he has given you is original temperature is given, change in temperature is given. Suppose if I want percentage, then what should I do? I should just multiply this one by 100. So the fractional change in EMF is equal to change of temperature. How much it is? 15. By original temperature, how much that is? 75 into 100. You can certainly understand this one going 5 times. So 5 cancels here 20 times. So what percentage you will be having here please? 20%. So options you look at, second option is going to be the correct one. Percentage change in EMF is as well equivalent to percentage change in the variation in temperature. That is the point what you have to understand. Look at the next problem, problem number 15 this time. If pi is Peltier coefficient, heat evolved at a junction when a current of 10 milliampere passes for 10 seconds in joule is how much? Pi is Peltier coefficient, that is the point. What is the formula for pi first of all? Pi Peltier coefficient means it is Q by small q. That is actually formula. But what is small q? it is current into time, because small q is the charge. Charge is the product of current and time. So these are the values what he is talking. Now what is his question there? His question is this: heat evolved is how much? So you can write q is equal to pi into I into T. Now pi you take it as it is. What is the current that has been mentioned? 10 milliampere, 10 power minus 3. What is the time that has been mentioned over there? It is 10 once again. So you can cut these two here minus 1 time. So it should be pi by 10. It should not be pi by 100. It should be pi by 10. The very first option itself is correct for that. Answer is going to be the first one. It should be pi by 10. That is the point you have to remember. Look at the next one, that is question number 16, please. If the charge flowing through a metal rod is halved and the temperature difference across the ends of that rod is increased by 200%, the Thomson heat absorbed or liberated, what happens to that value? Thomson heat he is talking. That means you should immediately get to your mind, sigma is equal to q by q into delta T. Now let us write capital Q is equal to sigma q into delta T. So this is the first equation. Now look at the second one. What will be q dash now? Charge is becoming half, he said. Fine. Another thing is logically giving temperature difference across the ends of that rod is increased by 200%. That means suppose if earlier value was 100, now it is increased by 200. How much it will now be? It will now be 300 of delta T. If original value is 100, 200% more. That means totally it will be 300. So this cancels how many times, please? 150 times. So is it not 150 of q, please? Sigma q delta T is q. So 150 of q. Earlier it was q. That was 100%. Now what will be the percentage rise? 100 is become 150. That means what will be the percentage rise over here? It increases by 50%. So very first option is correct for this particular question number 16, please. In fact, by look also you can finalize that one. It is not a big task, right? Look at the next one, that is problem number 17. Match the following. He is just asking you list 1, of course he has given few physical quantities. List 2 he has given some units. Same question has been given in one of the EAMCET papers earlier. Thermo EMF. EMF will always be in volt. Peltier coefficient, that also can be in volt, but he has given one more thing over there, that is joule per coulomb. Thomson coefficient. Thomson coefficient can be taken joule per coulomb per Kelvin, otherwise volt per Kelvin. And joule heat, that heat always will be taken in calorie generally. So A is tallied with F, B should be tallied with G, C should be tallied with H, and D should be tallied with E. That is a correct pair, that is correct match in fact. So first option is correct for this question number 17, please. Look at the next one, that is question number 18. A copper constant and thermocouple produces an EMF of 40 microvolt per degree centigrade. The smallest temperature difference that can be measured with this thermocouple is 2.5 degrees centigrade when a galvanometer capable of detecting as low as 10 power minus 6 ampere is employed. The resistance of that galvanometer is how much? That is the concept. These types of questions are very commonly asked models at different entrance examinations. 40 microvolt per degree centigrade. That means for every 1 degree centigrade, it is going to be 40 microvolt, that is the EMF that is generated. That is what he is talking about first of all. And what next he is talking as such? The galvanometer can measure a current of 10 power minus 6 ampere. And what exactly is its resistance? Let us consider the resistance of this galvanometer, that is as R. Now, for 1 degree it is 40 microvolt. What is he talking? It can measure 2.5 degrees. 2.5 degrees centigrade when it wants to measure, what will be the total PD over here? 100 microvolt it should be, because for every 1 degree 40, 2 degrees 80, 2.5 degrees 80 plus 20, that should be 100. So what is the total PD across this system now? 100 microvolt. Come on, relate these things please. V is equal to IR, or else R is equal to V by I. What is V value that has been mentioned here? 100 into 10 power minus 6 by, what is I that has been given? 10 power minus 6. These two, they get cancelled. And what is the resistance of that galvanometer is our question. What is the concept over there please? It should now be 100 ohm. It should not be the first option once again. It should be the second option. It should be 100 ohm, not 50 ohm as such. For 18th question, look at that. It should be 100. This is the calculation for that, and that is the corresponding option for it. Look at the next one, that is question number 19. Antimony bismuth thermocouple generates a thermo EMF of 100 microvolt per degree centigrade when the cold junction is at 0 degree centigrade. A microammeter of resistance 100 ohm is connected in the circuit of antimony bismuth thermocouple. If the least count of microammeter is 1 microampere, the minimum temperature difference it can measure is how much? Simple logic once again. 100 microvolt per degree centigrade, that is the value given. That means for every 1 degree centigrade, it can produce a potential difference of 100 microvolt. That is the value what has been mentioned. Fine. What is the resistance of that value, that ammeter he has given? Look at, that is 100 ohm. And what else he has given you? It can measure a current of 1 microampere. That means what will be V now? Is it not IR please? Is it not 100 microvolt now? Look at, for 100 microvolt, what is the temperature it can measure? 1 degree. For 100, this value also, it can measure what temperature again? 1 degree centigrade only. So the option is going to be the very first one once again. So no need for you to calculate anymore. The same value is repeated here after calculating this V from the given data. That means both used to measure the same temperature as such. That is the concept of 19. Look at the next number, that is question number 20 please. A thermocouple produces a thermo EMF of 50 microvolt per degree centigrade. A thermopile of the two junctions are at 30 degrees centigrade and 50 degrees centigrade. If the thermo EMF generated in the thermopile is 100 millivolt, the number of thermocouples used are. How many number of thermocouples are to be taken up? Just a simple look at here. At 0 degrees centigrade, the EMF what is going to be generated is 50 microvolt. Excellent. But for 30 degrees to 50 degrees, that means for 20 degrees centigrade, how much is the value? Generally, we directly can take up, it is 50 into 20. What? Microvolt for 20 degrees centigrade. That means it is now 100 microvolt you have to think of. Now what next he is giving you? 100 millivolt is generated ultimately. How many number of these thermocouples we just want? So each thermocouple just gives you this much. Let us say there are n thermocouples there in that thermopile. That thermopile can measure how much value he said? 100 millivolt. That is what has been given. So what will be n now here please? 100 into 10 power minus 3 by this value of 100, this value of 100, what? Microvolt. That of course 10 to the power minus 6 into 100 once again. Now you can cut this one over here. How many times? Minus 4 times. This of course minus 1 time. So this of course minus 3 times. So if you are taking each one 10 like, then how many thermocouples you require over here please? Exactly 100 thermocouples we require over there. The third option is going to be the correct option for this question please. Look at the last number in this order please. Keeping the cold junction at 0 degrees centigrade, thermo EMF due to a thermocouple is same whether hot junction is at 200 degrees or 360 degrees centigrade. Then its neutral temperature is how much? In fact, neutral temperature for a thermocouple is going to be constant, I have already told you. It is independent of cold junction temperature, that also I have told you. That means neutral temperature is said to be the characteristic temperature of a thermocouple. So, at 200 degrees centigrade, even at 360 degrees centigrade also, we people are finding the same value of that is keeping the neutral temperature is how much? Keeping the cold junction at 0, thermo EMF due to the thermocouple is same. This is the at 200 also thermo EMF is same, at 360 also thermo EMF is same. If EMF at both the temperatures is same, then neutral temperature will be theta 1 plus theta 2 divided by 2. That in the sense what? It will be the average of these two values, theta 1 plus theta 2 by 2. It is 200 plus 360, 560 by 2. So, you can write 280 degrees centigrade. So, just look at the 280 degrees centigrade where it has been given. The fourth option, that is going to be 280 degrees centigrade as such. So, these are the different models what we people are having as far as thermoelectricity that is concerned. But truly speaking, among all the chapters of electricity, this is the chapter which is the easiest, smallest and easy to score 1 mark in the final EAMCET examination by everybody. So, try to concentrate on all the formulae carefully, on all the models whatever we have discussed and other things like, and a bit of theoretical concepts as well if you learn. So, certainly you can score that 1 mark based on this thermoelectricity part as such.